Okay. Well, last time I said that I would give an example for the use of the edge with approximation, but in effect the same example is appropriate for discussing Nagar expansions for moments. So what I have in mind is that this morning I'll discuss in general terms the Nagar expansion for the moments of econometric estimators, and then we'll apply that to this example, at the same time generating the derivatives that we require for the edge with expansions. I think most of you have probably met the idea of the Nagar expansion, since it was the earliest finite sample approach back in 1958 in Econometrica. Just to generalize the basic idea, we're going to take some function e of our data second moments p, a vector of data second moments p, and of course it also may depend upon t and the assumed known parameters of the model generating the p. Let's simply write it down as depending on t. What we have in mind then is to take a Taylor series expansion as before, though I remarked that p are the data second moments. It's better to assume that you're taking deviations of these second moments from their expectations, so that you have the simplifying property, just from the point of view of notation, that the expectation of p is 0. Then, if we take the usual kind of Taylor series expansion, p being a matrix, we have to use a certain amount of notation here. One possibility is to write it in the form, say, s equals 0 to some upper limit r, and then simply have a kind of product of derivatives d p I, should we say, of e worked out at 0, of course a 1 upon s, and then simply the corresponding product of the p's. Now that is a rough and ready notation. There are better notations available, but perhaps it's simplest to spell it out a little, the usual kind of well, I suppose do two more just to etc. On the blackboard, at least I can use L without confusion, or too much confusion. And of course, what I'm doing there is to take the summations over all values of the suffixes, and this is the fourth order expansion. Now, if we're going to discuss the approximation here, what we would then do is to add an additional term, r little r, r4 in this case, And then we should consider taking expectations of this to get an approximation to the first moment, in which we hope that we will find that each of these terms is of lower order than the next earlier one, and that the r to the fourth, or the r to the r in general, is equally of smaller order of magnitude than the last retained term. And of course the difficulty with such assumptions is to actually prove that this is true for the remainder term, and I will discuss that considerably later. But just from the point of view of giving this example of how the thing works in practice, I'll leave that discussion until the next lecture. But this morning, let's simply assume that, for example, if we write this in the form, let me write it in the form E R P T plus R R, in other words, the stated terms plus a remainder, then the Nagar expansion idea is that if we're looking at the kth moment, we simply take the approximation is approximately expectation ER P T to the fourth, sorry, to the kth.
When it's little e, you didn't define it. That's beta hat minus beta, isn't it?
Yes, or any other function.
Sure. Oh, okay.
So it might be a t ratio. It might be anything, a test criterion which is distributed asymptotically as a chi-squared.
But you're saying this Nagar stuff can be applied to any.
Oh yes. Yes, the essential idea of the Nagar stuff is simply take any econometric estimator, anything at all, any function of the sample second moments. Well, there I'm really being much too restrictive. P can be anything at all, provided it's got enough moments, and provided they have the usual properties. The usual properties that one is going to assume is that if you take any product of P's up to, say, A terms, then the moment is order 1 upon T to the A. Sorry, 1 upon T to the half A. Now, that if the moment exists, that will usually be true for the second moments, defined as deviations from their mean, and if you apply it to not only data second moments but other similar things like higher degree moments of the data, you will usually find that the same property is true. So you can use this thing very generally. The essential point is that if this condition is satisfied, then the first term here will usually by definition be 0 because we're taking deviations from the mean. The second term will be of order 1 upon T. Third term of order T to the minus 3 upon 2, and so on. So that this is the essential property that we require in order that we can say that each term is of order, well, if it's the 8th term there, it's going to be of order 1 upon T to the square root of T to the A, So each term in the expansion is going to be of lower order than the previous one. No problem with that, provided the moments exist. The real problem is to argue that the remainder has the same kind of property of being of lower order than the terms you're retaining. Now, so in general, it's a rather powerful thing when it works, and very often it's the only way to get some idea of what the moments are. Very often, in the past, people have used these expansions and compared them with Monte Carlo simulations, usually to find that they work very well. And it's really only a matter of working out the terms in the appropriate Taylor series expansion in order to sort out what the approximation is, provided that you also know what your higher order moments are. And I will discuss that at the end of this period when I've given you the example of the application. The application, in fact, is the one contained in my 1976 article, March 1975 article, Econometric, where I'm discussing T-ratios of K-class estimators. Well, of course, the T-ratios was to show that you could use this kind of approach, which was the edge of the approximation in that article, to T-ratios. In fact, I shall stop at looking at the moments of the K-class estimators rather than the moments of the T-ratios, simply because the T-ratio expansion is 1 degree further in complication compared with the K-class estimator itself. But by the time you've seen how the K-class estimator thing is done, you can see how to extend it to anything appropriately. Well, okay, there's very little to this then, except the kind of general proof of the validity of the expansion, which I'll leave till next time. And so let me move on. Oh, except, yes, I ought to have discussed that when, of course, I've really discussed the order of magnitude for the case where k equals 1, because there one's simply looking at successive terms here, and one is just taking expectations term by term. But now, if you're going to look at, say, the second moment here, k equals 2, then clearly what you have to do is to consider taking the, I'm again going to cheat by not writing everything down again, taking this, which is by definition E4 PT, and squaring it. Well, clearly then, though there's only a finite number of terms here, there's something of a problem to square it out, and then having expressed it as a sum of, products and squares of the separate terms here, taking expectations of that term by term. But I think you can then see that, again, using this basic general idea, you can take expectations term by term, gather together all the terms that are of the same order of magnitude, and notice that you may be able to neglect some of the later terms because they're of higher order of magnitude than the limit, than the magnitude of the kind of first term that you're neglecting. for example, if E0 is of order 1, it may not be. If E0 is of order 1, it might be a function of t which is tending to 0 as t goes to infinity, because I allow the function itself to depend upon t. But if it's of order 1, then the first term in this square that you're neglecting is of order 1 product of this term with the next term in the expansion. In other words, in this case, it would be of order t to the minus 5 upon 2. And so you would then say, okay, are there any other terms in this product which are of less order less than or equal to e to the t 5 upon 2? Well, there are, because, for example, if you take the square of this term, it would turn out to be of order t to the minus 4. So you wouldn't need to include that term in the Nagar expansion for the second moment. You'd only return terms up to t to the minus 2. So a lot of these terms in the square would be not included in the summation for the square and would not be included in the Nagar expansion. And so on for terms of order, for moments of order k in general for values of k. Clearly you can do this for any moment, third, fourth, and in fact it's of some interest in some cases to work out the moments of order 3 or 4 to get an idea of the skewness of the distribution, or the flatness of the distribution for the function e. In fact, we have to do that in order to get the Edgeworth coefficients of a higher order in effect involve working out those kind of moments. Well, so let's take my example. The example is drawn from this paper of mine, and so rather naturally I'm using the same notation. It's not really the same as Nagar's notation, but the ideas involved are very much the same. We're taking a case where we're estimating by instrumental variables so we have an equation y equals xa plus u. X is made up of both y, which are the endogenous variables, and z1, which are the exogenous variables. And it's a classical case in the sense that I'm not assuming any of the z1s are like the endogenous variables. The z1s are just non-stochastic instrumental variables, if you like, predetermined variables. And I write the reduced form equations for the y's in terms of a complete set of z's in this form. Yes, and in fact, for simplicity, I've specialized on the case where it's two-stage least squares. So in other words, the z's, the complete set of z's that determine y, are going to be used as instruments. Well, likewise, just again for simplicity, if I look at x primed, I'm going to write that that is equal to qz primed plus v primed 0, where q is the reduced form coefficients p as the first block, and then the unit matrix which picks out z1 from the complete set of variables z, followed by a zero matrix. In other words, I'm assuming that z is z1 Z2, and then the partition here into I0 is the same as the partition here into Z1, Z2. That all simplifies my later notation a little. Then it's convenient to work. I said before I was going to work with the data second moments, but now I'm assuming that Z prime Z is a constant matrix, and it's convenient to work with the OLS estimates of Q, which can be written in the form x prime Z, Z prime Z inverse, and then we can split that into Q itself plus delta Q. The point about this, of course, is that in doing these Nagar expansions, we want our P to be such that its expectation is 0. And you see that by multiplying by Z prime Z upon T, well, alternatively we could divide both of these by T. Z prime Z upon T is assumed, for simplicity, it doesn't really make any difference to the theory of this thing, to be a constant matrix as T goes to infinity. X prime Z upon T is of order 1. Q is, of course, of order 1, but delta Q is of order T to the minus a half. So, in other words, I'm going to use the part of my P vector in my previous discussion is a vectorized version of delta Q. In the same way, it's convenient to work with a further the same kind of idea, but now using the, instead of using the reduced form for the Y errors, we're using the structural form errors. So Q is that vector. I always find it convenient to use rather a lot of notation because one is then going to simplify somewhat the formulae that follow. So let me then introduce the notation D to mean QMQ primed minus 1. The point of the minus 1 is that it's always the inverse of this matrix which is turning up in the subsequent formula. M, by the way, sorry, M is not defined yet. M is in fact what I'm using for Z prime Z upon T. And D hat to mean Q hat M Q hat prime inverse. Well, that's the notation that I'm going to be using. Now, A hat, by definition, the two-stage least squares estimator, in effect, can be written in the form well, of course, immediately we see that we've got D hat there. In the same way, if we take, substitute what Y is into the equation and take the corresponding term in A over to the other side, we see that we can also write, well, now I'll write it down in terms of D hat. Oh, I'm sorry, there's a minus 1 here. you've got d hat, and then q hat m times little q. Obvious way of expressing that. So this explains why one starts out by using these definitions of capital Q and little q. Now, of course, what we need is to expand that so that we have terms in little q and delta q being q hat minus q. And what one clearly wants is that each term is of higher power in delta q and q as one moves along the series. And an obvious first thing to do is to say that we can replace this by dqm little q into d hat minus d into qmq plus d hat q hat minus q, sorry, d hat minus d, q hat minus q, mq. If you simply cancel terms out which are the same in successive expressions, you get back to your original expression. Starting at the top end, cancelling out the q here with the q hat, q in the q hat minus q, then moving down to the next level. Yes, I'm sorry, I went too fast. I've skipped a line. That's all right. Cancel this with this, and then cancel this d hat q mq with the d hat q mq here, and you get the d hat q hat mq. So then in the next line we can now do what I did there. First two terms the same, and then plus d into q hat minus q mq, and plus d hat minus d q hat minus q mq. Well, the point of that manipulation is to notice that, first of all, the first term here is linear in the q and delta q, and so this term is going to be the term which is of order t to the minus a half. Then the next term, obviously the d hat minus d, we shall have to expand further, but it's going to have a difference there of order t to the minus half multiplied by q, which is t to the minus half, so a term of order t minus 1. Similarly, a term of order t minus 1 here, and then here a term of order t to the minus 3 upon 2. And that's as far as I'm going. I'm not going any further than t to the minus 3 upon 2 in this expansion. It's usually enough for us to work out the usual approximations to the moments required for the Edgeworth expansions that we normally use. Well, then of course one is going to have to take a corresponding expansion for d hat minus d, which is q hat m q hat prime minus 1 minus the same thing without the hats. And one way of writing that is to write it in the form minus q hat mq hat inverse into q hat mq hat minus q mq prime into q mq primed minus 1. Well, of course, this is d hat, this is d. In the middle we've got d hat minus d. It's a fairly obvious kind of result. And we can write it in the form minus d. Well, you see now we introduce q hat equals q plus delta q in here and get the obvious expression delta q delta q prime into d plus, so minus d hat minus d into the same thing, d. Yes, I mean, in order to make that more intelligible, let me replace that by square brackets and then say that we have the same thing in square brackets here as we have up here. Well, that's an obvious recursion in the sense that you can now substitute for d hat minus d the same expression as before and continue for as many terms as you like, and that will give you as many terms as you like in the expansion of d hat minus d, with a remainder, of course, which corresponds to the remainder on the Taylor series expansion. And in effect, what one normally wants to do is to get an accuracy of order t minus 1, so that the remainder is of order t to the minus 3 upon 2. And so one goes one stage further in this recursion. Perhaps I should note also, you see, that inside this square bracket we have a term of order t to the minus a half, two terms of order t to the minus a half, and one term of order t to the minus 1. And so if we're carrying out this recursion twice, we don't really need to carry this second term into the second term of the recursion. And so I will, at this stage, again, to save myself writing, simply say what that recursion gives you plus d, and then you have the first term here, which is delta q mq prime plus q m delta q prime, and then you have d again, and then you have the same thing again, delta q m q prime plus q m delta q primed multiplied by d, and then we can say simply plus, if you like, order delta q cubed. In other words, this again corresponds to the Taylor series expansion for d hat minus d up to the second order term. Now the reason I'm only going that far is because when we come to substitute into d hat minus d here, in all cases it's getting multiplied by a little q, and so we are retaining terms up to order t to the minus 3 upon 2 here. So now all we have to do, you see how complicated these expressions get, is to substitute d hat minus d as given by this into d hat minus d here. And we've got our total expansion of this order. Well, one sees why not many people take an interest in Nagao expansions. Shall I go further? Well, let me write down the whole thing in its final state, and you can check it yourselves if you care to. I think really the trouble is to have enough blackboard to write down all these formulae.
The blackboard the other one will slide over.
Yeah.
Possibly the one on your left.
Yes.
Probably use that in the training that developed in there.
Yes. Yeah, well, if you've got this expression for d hat minus d in your notes, the only thing is that I shall cover it up, but perhaps retain the formula here. So essentially what we're going to do is to substitute in there, start again then, a hat minus a equals, well, the first term is the same, dqm little q. Then let's gather together the second order terms and see what they consist of. Well, first of all, let's take this third term here. That's can be written simply as d, then delta q, and then m, and then little q. So that's the simplest one to think about. Then this last term here is obviously a third order term, so we don't have to think about that at all. But what we have to do is to substitute into d hat minus d. And since we're only picking out the second order term in the final expansion, we only need to take the first order term in that expansion to give us the second order term here. And if you pick out what that includes, you find that it has d into delta q into m q primed, and that's the d hat minus d times d, and then on the end of that there is q m q again, so that's q m q, and then the same term with the order of these three terms reversed, that is d into q into m into delta q primed, and then the same as before, d q m q. And that's all the second order terms we have in the expansion. So then we proceed to write down a whole set of third order terms. So all the remaining terms are third order terms. We first of all continue with that expansion for d hat minus d here, picking out now the second order term in that expansion, which is d delta q m delta q primed d times q m q. Then we substitute into here this last term for d hat minus d into this term, and that gives us plus d into delta q m q primed plus q m delta q primed into d into now the same thing again, delta q m q primed plus q m delta q primed times d, and that's the last term in that d hat minus d expansion multiplied by q m q. q m q. So that's finished that term off. then all we've got left is this term. Well, you see, in that term, we've got delta q and little q, so all we need is the first order term in the d hat minus d, and that gives us minus, yes, minus is right, d delta q m q prime plus q m delta q prime, the same as before, times d, but then that's going to be multiplied by delta q mq. And so that's the Taylor series expansion of degree 3 plus a remainder, which, as usual, I'll just write R3. Well, you see, though the theory is cast in terms of Taylor series expansions, when you get down to it, what it's really involved is approximations for matrix formulae of this kind. And now what we're going to do is to take expectations term by term in the usual kind of way. Before we do this, however, we can do a bit of cleaning up. What we can do to make things simpler is to introduce at this stage m q prime d q m. You notice that in fact this is m to the half times I minus m to the half q prime d q m to the half, all multiplied by m to the half, and that it's easy enough to show that the last term in the bracket is an idempotent matrix, so the whole thing in the bracket is an idempotent matrix, which is one of the standard idempotent matrices which turns up in this kind of theory, is all I can say. But it does, at the end, ensure that there's a good deal of simplification in some of these expectation terms. What we can then pick out is that you can, again, I'll leave you to check up that this goes through quite well. But for example, here we have m minus m q prime d q m, which is your L matrix, so that this can be written with only two terms, d into delta q LQ. The other term, I'm afraid, you can't do anything with at the moment, so you just have to reproduce it, and so on. Minus d delta q m q prime plus q prime m delta q as before, but then little l times q, plus d into q m delta q prime into d q m delta q d q m q. Well, so a good deal of simplification just by introducing L into the, or some simplification just by introducing L plus R3. Yes, I'm sorry, I've missed out a term. So we don't quite get away with everything, quite that simplification. dq delta q L delta q prime dq mq. Some simplification. Well, now, what we can now do from this is to pick out what the required first, second, third derivative coefficients are, and express them in kind of generalized matrix form. And that I will discuss a little later. But at the moment, let me discuss the kind of formulae required for the moments if we make the assumption that the errors are normally distributed. You see that my little q's and big q's in this case only involve just to write them down, z prime u upon t. Only involves a constant z and a stochastic u. But the great advantage of the Nago approximation approach is that you don't have to confine it to classical type problems, the ones I've been discussing. You could equally consider the case where the z's involve lagged y's and still work out all these formulae, and these would still be valid, provided you could extend the proof for the order of magnitude of the remainder to such a case, and provided you could work out what the expectations of the moments of the second moments. So, provided you could extend the formula for the moments of the second moments to cases of dynamic models. What I propose to do is to look at cases where the z's equally may involve stochastic variables, may involve lag-dependent variables, and so on. And what I want to draw your attention to is a little known formulae. Which can be used wherever you have products, moments of normal variables, normally distributed variables, or in other words, the expectation of products of normal variables. And though this is quite often used, I don't know who first discovered this. You will find it in some textbooks of mathematical statistics. It's easy enough, really, to derive from the approach using the moment generating function for multivariate normal distributions. But I might as well say what it is in a very kind of general context. Suppose you have a product of n normally distributed variables. What is its expectation? Well, the formula, oh yes, and with the limitation that expectation xj equals 0, in other words, they're zero mean normally distributed variables, but otherwise they have a general variance matrix. Well, the formula that is useful is that you take the product, the sum of all products of this form what I should say is equals 0 if n is odd, well-known property of normally distributed variables. But if n is even, then you take all partitions into pairs, so the sum is over all partitions into pairs. For example, if you, this is the best known case, which is very frequently all that you need to know. If you have the product of 4 such variables, then you have to take just 3 partitions. Why don't I write it down explicitly? xi, xj, expectation, xk, xl, plus expectation xi, xk, The 4th order case is very simple because there are only 3 partitions. If you go to the 6th order case, there are 15 ways of splitting it up into 3 pairs. And so you have 15 terms to take account of. Now the thing is, with normally distributed variables, one is simply looking at the covariances. The covariances are, what define the distribution. And so it's not too difficult to use such a formula. You just get rather complicated sums of possibly, in this case, 3 terms, but as you go up into 15 terms, next stage is 105 terms, and so on. It gets that you've got rather a lot of terms to take account of. But this is type of formula is quite useful in time series approximation work too, where typically you have the serial covariance matrix, and you then can use this to work out what the expectation is. Of course, you then are going to get into more complicated summations, because typically, of course, you're going to be taking, say, the second moments of, say, which involve 2 normally distributed variables, and you will have to do the summation over different values of t for all possible values of t in working out those second moments. So you will have to take summations of formulas of this type. But that will only involve taking summations of products of covariances in this kind of way. Well, so that's the kind of typical formula that may be used, and of course then you might want to consider formulae for matrices of the following type. Suppose now that we look at this kind of formula, xa, x prime b, xc, x prime. I'm using x's in quick succession to mean rather different things. Here I have in mind simply a case where the x's are the kind of covariance matrix which often arises, data second moment covariance matrices, where you have something like expectation xij xkl is a product, a chronic product type of thing. So X is a second moment of the data matrix, where I, for example, might be the number of the variable and J might be the time period, and then you're making some kind of assumption that you have serial independence, for example, so that the result comes out as a product of this kind. That very often happens in this kind of work. Well, what I've done is to look at the case where you've got a fourth moment of the second moment matrix. You have a fourth order term in an expansion involving such a second moment matrix X. And this is just to illustrate the kind of technique that's involved. In fact, one sets out simply using suffix notation. It's amazing how often you start out with a matrix expression like this and then have to turn it into suffix notation. And just again to illustrate, one can write this in the form looks tremendously complicated, but of course all it is writing down successive products, taking account of the fact that you have some of these transposed, which ensures that you have an XKS here instead of a XSK, and so on. And so all you're going to do is to take expectations of that and then use this kind of formula here to say that in effect you split. By the way, I haven't said explicitly that I'm using suffix notation here for the summation, which means that I should be writing in front of all this summation with respect to R because you've got a repeated suffix R, summation with respect to S because you've got a repeated suffix S, similarly summation with a K because we've got a repeated suffix K, and so on. So wherever you've got a repeated suffix, you are going to take the summation. That explains why this is the formula for the this product. Well then, within that notation, what we're then going to have is three terms. We can change the order of the factors without affecting the meaning of the formula. So let's take first of all the XIR with the XKS, giving us expectation XIR XKS. Then write down the following terms ARS BKL. Then we must take the XLU with the XJV. That's the only remaining pair. So let's write that down next. XKS XJV. And then finally we end up with this CUV. CUV. That's.
You're going to XKS twice now?
Have we indeed? Yes, we have indeed. It's XLU. XLU. I'm sorry. XLU. XJV. That's supposed to be V. Well, it's obvious what the other two terms will be on the same basis. Let me move back again, clear blackboard, and write down the remaining two terms. Plus expectation XIR XLU, and then as before ARS BKL, then expectation XKS XJV, and CUV again at the end, CUV, plus expectation XIR XJV ARS BKL, expectation XKS XLU CUV. And then all we have to do is to substitute this formula, or its equivalent, in all these expectations, and then turn the formulae which involve suffix notation into matrix. Okay, well, let us then translate this back into what expectation D would be. And you see that because we've got an omega RSY and A, yes, we have two formulae of the following kind: omega UV C UV, and if you think about that, that's just the product of the omega UV by the transposed C, the omega by the transposed C, and then the trace has been taken. The same has happened here, and so we can write trace omega A primed, trace omega C primed. What do the remaining terms give us? If you sort them out, you'll find it's sigma B sigma. Now, doing the same thing here, the one that you notice is well, we have sigma IL sigma BKL sigma KJ, and that must mean that you've got sigma B primed sigma as, if you like, the matrix element there. The rest of it makes one large trace because it's ARS and then omega SV, then CV mu transposed, and then coming back to omega RU again, and that corresponds to trace A omega C primed omega primed. I haven't yet assumed that omega is symmetric, but of course it must be. So that prime can be removed. Then finally we're going to have plus sigma, and then trace sigma C primed omega primed A primed as one trace, and then a second trace, trace B times sigma primed. Again, we can remove the prime and the omega. Well, this is just illustrating something which you really don't wish to know very much, how to derive such formulae. But there are such formulae available for any kind of product of this kind, and so it often turns out to be convenient to have a list of such formulae, and then one can start taking the moments, the first moment in particular of this kind of expression, but higher order moments also, provided that your delta q's and q's have the kind of properties required by the assumption here that the x's have. Now, in this case, the case I've discussed already, in fact, the sigma ij corresponds to the variance matrix of the b's and the u's together. The omega jk corresponds to the m that we have here, and so it's quite easy to make use of such formulae to derive the required moments. Well, though I say that this is intended to be a kind of detailed example, I'm afraid I'm going to skip the detail of that because it's in the paper and it's in some of my earlier papers, and of course it's really rather a fairly a straightforward application of this kind of formulae to get the moments as given here. Now, what about the application to Edgeworth expansions? Well, there, again, the matter is not absolutely straightforward. If you consult the paper here, you find that as with the Nagar expansion, but in a rather more complicated form, you have to be considering the derivatives, which I denote usually by, as before, by for the derivative with respect to pi, pj, bk, I simply use the suffixes ijk to denote that derivative. That what one finds is a series of intervening expressions of the kind that we take products of the EIJK with various moments or cumulants of the distribution of the P. Now, if we, for example, take a third order cumulant, what we are then doing is to think of the corresponding derivative of the function that I previously denoted by eta of s, where sorry, I shouldn't write down any equality. Eta s was log phi s, which phi s was the moment generating function, in other words, the expectation of e to the s prime t, sorry, s prime p. So p are the second moments concerned. S primed is a vector of the same dimension as p, and we're defining our moment generating function as phi s. Of course, phi it is the characteristic function. Characteristic function equals phi of it. That's just to remind you of my previous notation. Then e to s is the cumulant generating function, it's just the log of phi s. Now then, my kappa ij is just the same as d cubed s phi d sj d sk. In other words, it's just that is by definition the third order cumulant with suffixes I, j, k. Now the Gram-Charlier expansion, or the Edgeworth expansion, typically involves taking products of the derivatives of the E function, the function defining the econometric estimator that we're interested in, and then taking various kind of intermediate expressions which involve, for example, this kind of summation, and labeling it, I typically call such intermediate expressions as this alphas. So in fact this would be, for example, alpha 9, or whatever. You gather from the fact that I'm using numbers as high as 9 that there are rather a lot of alphas. For example, in the paper that I'm looking at the moment, I had 19 such intermediate expressions, and then one finds that the Edgeworth coefficients are in fact simple functions of these intermediate alphas. So you have a set of alphas defined in this kind of way. Or, for example, as you might have a formula, the form, say, alpha 10 is E I j k l kappa I j kappa k l, and so on and so on. In fact, in getting an Edgeworth expansion with an error of order t to the minus 3 upon 2, one finds oneself working with the derivatives up to the third order and the cumulants up to the fourth order. So I've really given you a formula for an alpha which doesn't occur in the particular expansion up to errors of order t to the minus 3 upon 2, but that sort of thing occurs if you go to higher orders of approximation in these expansions. So typically what you're finding is that you have to sort out what the derivatives are from expansions of this type. Well, now what you notice is that if you think of your p vector as being made up of first of all q and then vec delta q, that though the derivatives are going to be symmetric with respect to the variables, with respect to the elements of this vector, if you look at, say, the third order term here, which involves a product of a delta q with a Yes, a delta Q with another delta Q with a little q, there's no kind of symmetry there. And that one way of looking at that is that you can think of such an expression as being a polynomial, say a third order polynomial, in P. And in other words, it can be written in the form of a phi I j k p I p j p k, with the phi I j k not being necessarily symmetrical with respect to permutations of its indices. Now, the question is, what is the corresponding third-order derivative matrix? And of course the answer is that if you differentiate, you're going to find that you get all possible permutations of the ijk, so that the corresponding eijk, the corresponding third derivatives, involve all possible permutations. So can be written in the form phi ABC, ABC permutes ijk. That gives you one further level of complication in using these formulae, because then you have to think what happens if you substitute such a phi ijk, and clearly one has to think about all ways of taking a given expression here and changing the order of the variables occurring in the expression. And so indeed one finds oneself faced with a very considerable organization problem to sort out what the required alphas are. This again is kind of illustrated in the back of this paper. And of course what it would be very nice to do is to have computing algebra programs do it for you. And it would be a great advance in this field to ensure that instead of the econometrician or the econometric theorist going through all these kind of routine manipulations of algebra, if one could get a computer program to do it. It's one of the things that I plan to do in my retirement, is to find the time to try and get something organized in the computing field using an extended form of existing computer algebras.
I think there's a software called Reduce in America.
Oh yeah, sure, and there's Maxima. But none of these actually are sufficiently detailed in their matrix algebra aspects. They're really rather limited in what they will do for manipulations of matrix algebra.
MIT symbol manipulator.
Yes, well I think that is known for short as Maxima, M-A-C-S-Y. MAC stands for matrix, but in fact it doesn't quite do enough yet. It's a question of whether one can slightly extend it. But that is certainly something to be done in the future, and is not available yet. I always think that these things are on the verge of being extended in this direction, and yet it's for a long time they've been in that state without actually having the extension required for this sort of thing. Well, at this stage, we really have got to about the end of the period. Are there any further questions on what I've been talking about?
There's some paper on the NAGAR expansions. If I can remember it rightly, he commented on the existence of moments and the convergence of series and that sort of thing.
Yeah.
Your subsequent paper showed that the Srinivasan thing wasn't valid, or?
It showed that on the whole he was rather too pessimistic. What my paper was designed to do, and as I say I'll talk about it tomorrow, is to show that usually if the moment exists, then the Nagar approximation is a good approximation, a valid approximation. But of course that does depend upon, when I say usually, you have to have fairly strong assumptions for that to be true, but fortunately those assumptions are usually satisfied by the kind of estimators that we're interested in. So in effect, this type of expansion can be used quite generally. I ought to make one further comment. It's been known for some time, and Bhattacharya in Sankhya has given a very general proof of the result, the fairly obvious result, that the Nagar moments are really moments of the edge of expansion. They're both based upon the same kind of expansion of the E as a Taylor series expansion. Therefore, even if the moments don't exist, you can interpret the Nagar moments as throwing light upon the edge of the expansion. Since the edge of the expansion is a good expansion, it may be a valid expansion. Valid, what does that mean? That the errors in the edge of the expansion are of the correct order of magnitude as t goes to infinity, despite the moments not existing. So you can think of the Nagar moments as still throwing some light upon the asymptotic, upon the finite sample approximate distribution, the edge of the approximation to the finite sample distribution.
But what you said doesn't make the edge of the expansion suspect. I mean, you use the result of the relationship between Nagar moments and the moments of the edge of the expansion to give some credibility to the Nagar moments, even when they do not exist.
Yes, that's right.
But that wouldn't be used the other way around?
Yeah. Well, perhaps to, again, it's this sort of thing that you're looking at probability E of P less than R, and for any finite R, if T is sufficiently large, you can approximate with a corresponding edge of the expansion. So, shall we say we've got an edge with approximation? I better not use E for edge with, simply F R of little r. I've got too many R's. Okay, little r. For a kth order edge of the expansion, plus a remainder, Rk. Well, now what you can say is that for any finite little r, you can find Rk and prove that Rk is less than, say, t to the minus half k plus 1. But then you have some constant in here, little c. Unfortunately, that depends upon little r. So for any finite r, you can find such an order of magnitude, and C of r is depending upon r, and may go to as r goes to infinity, may behave in such a way that there isn't any finite moment. But you see, what will very often happen is that if you take fk, the f of r minus fk upon r, you will find something like the following, that it behaves like, say, 1 upon r to some power little s. That determines what order of moment exists. But then that is going to be multiplied by something which is really quite small, say exponential minus k upon kt. I've got another k here, capital K this time, capital K. So that as t goes to infinity, this becomes really very small. But still, because it's of order 1 upon r to the s, it ensures that the s plus 1th moment, or the sth moment, doesn't exist. In fact, it ensures that the s minus 1th moment doesn't exist. So that's really the way it behaves, that this remainder here is behaving something like this, but then it's being multiplied by a factor which involves coefficient which involves t, so that it's relatively small in terms of orders of magnitude in t.
I mean, within the symptom of tail, isn't you're interested in R which are very large.
Yes, yes, yes. Oh well,
Or small.
yes, yes.